So we got the test for 6.5 types of radiation, and the first question says radiation from the sources X, Y, and Z pass through the substances below. Each source emits only one type of radiation. Now what that means is each source is only producing one type of radiation. What that doesn't mean is that it can either be alpha, gamma, or beta. So you can use gamma, beta, or alpha, more than once here. Now you can see X goes through the paper, so it's not going to be alpha. It goes through the aluminium, so it's not going to be beta, but it's stopped by the lead there, so it must be gamma. And then Y also does the same, but it goes through lead this time, and that confuses a lot of students. But you know, remember, gamma is stopped by a thick layer of lead, and there's different frequencies of gamma. Gamma is an EM wave, and you can get really penetrating gamma and less penetrating gamma. So this looks like a really penetrating gamma with a high frequency, and it goes through the lead. So this one is gamma as well. And then this one is stopped by paper, so it must be alpha. Okay, and that's your 3 marks there. Just a process you need to think through. State the precautions that are taken to protect yourself when you're working with radioactive materials. So it's with 2 marks. I've put 4 here. So reduce exposure time. So try not to be exposed to that radiation too long. You can wear protective clothing. So depending on which one you're dealing with, whether it's alpha or beta, there are things, because we know what type of materials stop that radiation. Monitoring equipment. So often you will see people that work with X-rays wear a little badge to so that they know how much exposure they've had to a particular radioactive element. And then handling equipment. So you can use specialized equipment to move substances and to work with substances. And that was another 2 marks there. It says question 2 here. Isotopes of iodine can be used to study the thyroid gland in the body. A small amount of this isotope is injected into the patient and the radiation is detected. So this is a tracer. The 2 isotopes that are used is iodine 123 and iodine 131. So these are an isotope, remember, has the same atomic number, so the same number of protons but a different number of neutrons here. So this is a heavier iodine element. Answer the following questions in terms of number of particles. State one similarity between the nuclei. Now, so don't say same amount of electrons, even though 53 does represent it's a proton number, it's an atomic number, but it has got they've both got 53 electrons because they're both the same element. But the fact that it says nuclei, you need to state that it's got the same number of protons, which are 53, or you could say the same atomic number. State one difference, so they got a different number of neutrons, and we can work that out by 131 minus 123. You can even give the number of neutrons there, but just saying that they've got a different number of neutrons is fine. And then it says the nucleus of 131 iodine decays into xenon by giving out a beta and gamma radiation. What is beta radiation? Well, beta radiation is when it releases a fast-moving electron. And then we've got a bit of an equation going on here, which is the beta decay. So the way you need to do these is this side. So the arrow in maths we use an equal sign. In science we just use this arrow. So this 131 and 53 is equal to this. Now you can see that beta and gamma, so gamma doesn't release any particles, it's just a wave. That's just there to kind of throw you off. But this beta particle, because it releases an electron, so it's -1, it picks up a -1, electrons are negative by the way. We don't gain any neutrons or anything, so the mass number doesn't change. So the best way to do this for 2 marks is 131 plus 0 is going to equal 131. So if that was 1 there, it's not ever going to be 1, but if that was beta 1, or if this was alpha decay and that was a 2 there, or a 4, sorry, I should say, you would need something plus 4 to equal 131. So if this was alpha decay, this would be 127 plus 4 equals 131. I hope I haven't confused you there. But this side always must equal this side. And you can see there, 54, xenon has, because it's the element that's in front of it in the periodic table. If you look, you've got iodine and then xenon with an atomic number of 54. So if iodine turns into xenon, 54 minus 1 equals 53. And that's the best way to do these. Look at your numbers, and they must always equal this on that side. So it can never be a plus 1, because 54 plus 1, so there's your plus there. 54 plus 1 would be 55, and that doesn't equal 53. So the only way you can do is 54 plus minus 1 is going to give you 53. 131 plus 0 is going to give you 131. I mean, this question won't come up like that, but there will be a question. That's why I spent so long on that question there. These are quite easy to get marks if you understand what's going on, and you just need to know that this side must equal that side. Anyway, on to the next question. The isotope iodine 123 decays by gamma emission. Explain why it is a better use than 123 as a medical tracer. Well, gamma is less ionizing, and this is the other thing that we get confused with, is because gamma is the most penetrating, I suppose is the most dangerous really overall, inside the body it's the least ionizing. So it's the most penetrating, it's the least ionizing. Ionizing means the ability to strip electrons, really, or to strip the atom apart. And if you think alpha is the one with it releases 2 protons, 2 neutrons. So it's that positive charge. If it releases that proton, it's going to have because it releases a positive 2 plus positive. The atom itself then is going to be 2 minus, so it's going to be negative, and it's going to want to pick up 2 protons from somewhere else, and that's why it's the most ionizing alpha. And then you've got beta, which releases an electron, so it becomes positive. The particle becomes positive, or I should say that electron is looking to pick up protons from somewhere. But alpha is the most ionizing because you've got that 2 protons looking to get those negatives. I mean, it's a helium nucleus just looking for electrons, and it's going to strip electrons from your cells and mutate your cells. Whereas gamma is a wave, and it is dangerous because it's very penetrating, but it's less ionizing. Hope that makes sense. This question again, I mean, this is going to be a long video because this is a beast of a question. A radiation films badge, so that it's just something to monitor. So this is what we were talking about earlier. These medical staff use these monitors just to monitor the radiation. Sorry about the quality here. Is used by scientists who work near radioactive materials. The badge consists of 4 windows behind which the radiation sensitive film. So each badge is expected, blah, blah, blah. So what we've got here is your uncovered window A. So that will allow all radiation through, every single bit. Okay, so that we know what we're dealing with. If we look at table A, it's got 9,500 counts of radiation. So that's going to be the highest. And then each window then will have a different, so you've got the thin card, which is the paper, really, that's going to stop the alpha. And then over here, you're going to have the aluminium, which is going to stop the beta. And then you've got the thick lead then. Oh, well, it says thin lead, but, you know, hopefully it's going to stop the gamma, so we know exactly what's going on. We can take readings from this. So let's go to the question. What is the purpose of having the uncovered window in A? So it's detect the actual amount of radiation given off, so the total amount, and it acts as a control, I suppose, because you know what you're starting with. And that will allow alpha, beta, and gamma through. So that's all types of radiation. Then you've got window B, and it wants to know what types of radiation is detected? Well, on window B, sorry, I thought I had the pointer then, it's covered with aluminium. So it's going to detect two types of radiation. It's going to detect the beta and, oh, sorry, in this course, I got it wrong there. So this is going to, because it's aluminium, it's going to block the beta and it's only going to detect gamma, of course, because it's aluminium. So I've put gamma there. Whereas in C is the one that it allows beta and gamma because it's only stopping, because it's thin card, it's only stopping alpha. So that's why we've got there beta and gamma, because it allows those through. Just like the control window, well, there's no protection, it allows all of them through. Because it's only paper, it's going to allow the beta and gamma through. Whereas that B is only allowing gamma because it's got aluminium. And then hopefully window D then, because it's a thin amount, of lead, it's going to still detect some gamma. So there's your 2 marks for filling in that. I think that is, once it's broken down, the 2 marks are possible. This is the tricky question. How many counts were produced from just beta radiation? And now you're going to have to go to your table and you're going to have to work out now what it's asking. So if we start with 950, so that's not going to give us anything because we can't work. That's giving us everything. It's giving us alpha, beta, and gamma. What we need to know how much gamma is being produced, how much gamma and beta is being produced, and then take a 1 away from the other. So if you know that beta and gamma produce 6250 counts per minute, okay, that's just beta and gamma, and then gamma on its own produce 5500, you can take 5500 away from the 6250, and you can get what radiation the beta was, so how many counts per minute radiation of beta was. Difficult question for 1 mark, but again, it's just a process of working it out. Probably going to have to do this video in 2 sections, so I'm going to stop there